Okay, so here's where we're going. We know how to solve for a resultant vector when the components are perpendicular to one another. It's Pythagoras. It couldn't be a whole lot easier. We've also got exactly 2 components. Easy peasy. What if we do something crazy like throw that in? And suddenly our resultant is, whoops. Suddenly our resultant is here. That's not a simple Pythagorean solve. Or what if we do something like, they set out at 15 degrees east of north, then they turned and they went back this way. What's the resultant? Oh, okay. This takes a little more work. The other ones are the things that you started off with doing graphically. Plane goes 300 meters along the runway, then takes off at 38 degrees. What's the resultant displacement? Well, it's that. But we can't just do Pythagoras on that. So remember how I said these are all about finding the triangle? All you got to do is find multiple triangles. Add them up. When we have vectors that are not perpendicular, we find the x and y components of each vector. We add those up. We get an overall y displacement and an overall x displacement. Then we use Pythagoras. So it's just a multi-step process. These problems are more bookkeeping than math. They're math, don't get me wrong. But it's all about how good you are at bookkeeping and keeping your details. If you are a visual learner, oh my gosh, grab the colored pencils. You're going to need them. And I'm actually not going to start you off on sample problem 3C. I want to start you off on one that's a little bit more straightforward, and then we'll do 3C, because 3C is a real booger. I don't know why they throw that at you first for this kind of problem. So let's do one that's more straightforward that I'm going to make up off the top of my head. We'll use the roller coaster. Roller coaster moves 83 meters horizontally, then travels 45 meters at 30 degrees above the horizon. What's its displacement from its starting point? Now, you've already solved this using graphical techniques. Now we're going to do this using algebraic techniques. So here's the thing that you always start with these, and this is critical. You're kind of working backwards from this point. The resultant is equal to the square root of delta x total squared plus delta y total squared. That subscript t is important, because you're going to have delta x1, delta x2, in some cases delta x3 or delta x4, and you need to go back to get those totals. So this has outlived its usefulness. I can cut this now. I always start by putting this somewhere, because that reminds me that I need to find those. Now, I'm going to do this further. Delta x total equals delta, in this case we only have 2 displacements, delta x1 plus delta x2. Delta y total equals delta y1 plus delta y2. And I'm going to add in some other color coding. I'm on a white background, so hopefully it's okay. I'm going to color code all the motion for the first leg in this dark blue. Not real distinguishable from black, but we don't need to distinguish it from black. We just need to distinguish it from red. And then I'll use a bright green for this second leg. So I've got, and I typically put in something like, well, D1, and then all my calculations for that first leg, I'm going to box up in that color. So for D1, I've got delta x1 equals what? What's the x component of that first displacement? 83 meters. What's the delta y1, the y component of that? This is an easy one, guys. 0. There is no y component. It's moving on the horizontal. There is no y component to that motion. Okay, so I've got those set aside. Now for, move this over a little bit. Now for the second displacement. So I have delta x2, delta y2. I'm going to write here d2. Now I've got my angle. I can see that x is adjacent and y is opposite. So I know I'm going to use cosine with my x, I'm going to use sine with my y. That's pretty common. It's not a hard and fast rule. I'm going to switch over to black because I think that green is kind of tough to read. So cosine of 30 times d2 equals delta x2. So I've got a raw number here. I'm going to do something else though, especially when you're tracking multiple component vectors. I'm going to draw myself a little arrow there, just over my raw number, because that's a reminder to me which direction this is going in. In this case, we don't have anything that's opposing the initial motion, so we don't have to worry about signs, we don't have to worry about subtraction. But we will get those. We'll actually get them in the sample problem we do together. Okay, now I know that sine theta times d2 is going to give me delta y2. So sine of 30 times 45 meters equals delta y2. So I get a raw value, and it's nice, it's neat, 22.5 meters. And note that I put that little arrow in there to remind myself that this is 22.5 meters up. Okay, so what am I going to do next? I'm going to look at my overall triangle. So when I talk about my overall triangle, I'm talking about this as my resultant, this as my x displacement, this as my y displacement. It is kind of layered, it gets kind of messy, I understand. So I know that delta x total equals delta x1 plus delta x2. In other words, delta x total equals 83 meters that way plus, and remember that you're not going to round until the very, 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 very last step. So I'm going to keep that whole number, 38.9711, also that way. Move that up and shrink it a little bit. So delta x total equals, and they're both in the same direction, so I don't have to do anything in terms of moving stuff around, plus 83. I get 121.97 blah 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 meters that away. So I've got my delta x total. I'm going to shrink that just a little bit more. Now I need my delta y total. I love it when one of the component pieces is 0. It makes life so easy. So delta y total equals 0 meters plus 22.5 meters up. In other words, the entire value of delta y total comes from our second displacement. So delta y total equals 22.5 meters up. Okay, we've got our delta y total, we've got our delta x total, which means we can go back to that thing we started with, and we can plug in values. So resultant equals square root of, and yes, I am putting in that whole darned number, 9711 blah 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 meters squared plus 22.5 meters squared. I'm going to take the square root. That's where using the multi-view calculator is great, because you can just keep that number, pull it right down, square it, and put it right in. Let's get a raw number. Okay, I get a resultant value of 124.029 blah, 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 blah meters. I'm not done. What else do I need? I need a heading. I got to have a heading. And that heading, of course, is going to be the angle formed there between our resultant and the ground. So I wrote this up as theta equals inverse tangent opposite over adjacent. But then I'm going to get rid of that opposite over adjacent. That's just to help remind me that I'm looking at opposite over adjacent. When I look down here, I'm going to realize that delta y total is my opposite, delta x total is my adjacent. And I'm going to get rid of this altogether. Eventually, you will not even write that. You'll just go straight to writing delta y total over delta x total. Don't just write x over y or y over x, because sometimes it's acceleration on the y, sometimes it's velocity on the y. So make sure that your variables mean what they really are, that you say what you mean, that you write what you mean. This is about bookkeeping and accounting. Okay, so theta equals inverse tangent, and remember, I am not going to round these numbers. 22.5 meters over 121.9711 blah 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 meters. What's my theta? I get a raw answer of 8.9968. What would that actually give me for my final answer for this whole mess? 3 sig figs, 2 sig figs. 120 meters at 9.0 degrees where? North of east? Oh, really? Okay, what did I screw up? Hold on. Yeah, that's not the right heading. So a fair warning about your calculator, the multi-view calculators. The one thing, I love the multi-view calculators, the one thing that I have found that they are a little funky with sometimes is handling numbers in scientific notation. And it actually gave me my 121.97 in scientific notation for no good reason whatsoever. It just did. And that's what I pulled down and used. And I think that's what did it. So, okay, raw answer 10 point, and it's giving me that in scientific notation too. 10.45, what? Okay, blah, blah, blah. Okay, so we would have to make this 1.0 times 10 to the first to get 2 sig figs. And what's our heading? What's your heading? Above the horizon, above the horizon, above the horizon. So 120 meters at 10 meters above the 10 degrees above the horizon. Yes, you can put degrees in scientific notation. Seem clear? When you're doing these on real paper, I will tell you that my standard setup, and you can do what works for you, but remember, this is more bookkeeping and accounting. I put my picture dead in the middle of the paper, and then I can draw a little line out to a box that's got all my calculations for displacement 1, line out to a box that has all my calculations for displacement 2. I save one side of the paper for, R equals delta x total, blah, 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 and run all those down one side. And that keeps it reasonable. I'm pretty visual. I will sometimes color code my little boxes. I'll draw my triangle over, my first displacement triangle over in one color, and then I'll circle all those calculations in one color. Another note, when you're doing these on quizzes and tests, and it saves my sanity, but it saves your sanity too in the long run, circle those intermediate answers, because that helps me go back and find those. If you screwed up and you added your delta y 1 and your delta x2 for your delta y total, but you've got all those intermediate answers circled, I can give you more points. I will also say that if you circle all those intermediate answers, you're less likely to make that mistake. So, like I said, it's a bribe, but it's a bribe for your own good. Let's do the practice problem, and we're going to I'll stop this video to keep it short, and we'll do that as a separate one.